You're standing on a construction site, looking at a trench filled with rebar or a massive pile driver hammering steel into the earth. This is the moment of truth, where the abstract lines on a structural drawing meet the reality of the ground. The foundation is the literal and figurative base of every building, bridge, and tower, and choosing the wrong type is one of the most expensive and dangerous mistakes you can make. So how does an engineer decide between a wide, shallow mat and a deep, slender pile? The answer lies in a simple but profound principle. The foundation is the translator between the structure and the soil. It must take the concentrated, high-stress loads from the columns and walls and spread them out until the soil can comfortably carry them without excessive settlement. In this video, we're going to categorize and explain every major type of foundation. We'll start with the simplest systems for good soil and progress to the massive engineering solutions for terrible ground, explaining the structural logic, the construction sequence, and the pro tips that ensure a stable and durable base for any structure. Let's begin with the broad category of shallow foundations, used when stable, load-bearing soil is found within a relatively short depth below the ground surface. Their key characteristic is that their width is typically greater than their depth. The most basic type is the isolated footing, also known as a pad or spread footing. Imagine a single column carrying a heavy load. An isolated footing is a single, wide block of concrete, often square, that sits directly under that column. Its job is to spread that concentrated load over a large enough area so that the pressure on the soil is reduced to a safe level, known as the allowable bearing capacity. You'll see these under the individual columns of a framed structure. A pro tip from site engineers is to always pour the footings on undisturbed soil, never on backfill, and to ensure the bottom of the footing is below the local frost line to prevent frost heave. Next, for load-bearing walls, we use continuous strip footings. This is a long, continuous strip of concrete that supports a wall, distributing the linear load evenly along its length. It's the standard for residential masonry and concrete construction. When columns are too close together or the soil bearing capacity is low, their individual isolated footings would start to overlap. The efficient solution is to combine them into a combined footing. This is a single, large concrete pad that supports two or more columns. A special case of this is the strap footing, where two isolated column footings are connected by a concrete beam or strap to help balance uneven loads and prevent overturning. But what if the entire site has relatively poor soil, or the building is so heavy that individual footings would cover most of the site? Then you step up to the most powerful shallow foundation, the raft or mat foundation. This is a giant, thick, reinforced concrete slab that sits under the entire footprint of the building. It acts like a single, monolithic footing, distributing the load of every column and wall over the entire area. Like a raft floating on the soil, this is a common solution for high-rises on soft clay or for structures where differential settlement must be absolutely minimized. A common and catastrophic drafting mistake is to underspecify the rebar in a raft foundation, especially at the column connections where punching shear is critical. Now, we move into the realm of deep foundations, used when the suitable bearing stratum is too deep for shallow foundations to be economical or practical. Deep foundations bypass the weak, compressible soil near the surface and transfer the building loads to deeper, stronger layers of soil or rock. The most common type is the pile foundation. A pile is a slender, column-like element made of steel, concrete, or wood that is driven, drilled, or jacked into the ground. Piles work into primary ways through end bearing, where the tip of the pile rests on a hard layer like rock, acting like a column, or through friction, where the surface of the pile grips the surrounding soil, transferring the load through shear stress along its length. Driven piles are prefabricated and hammered into the ground using a massive pile driver. This process is noisy but fast, and the act of driving actually densifies the soil around the pile, increasing its capacity. A pro tip during pile driving is to monitor the set, which is the distance the pile penetrates with each hammer blow. A high set at the end of driving indicates the pile has reached a firm layer. For sites where driving vibrations would damage adjacent structures, or where the depth to bedrock is extreme, we use drilled shafts, also known as caissons or board piles. This is a clean hole method. A large, truck-mounted auger drills a deep Cylindrical hole into the ground. The hole is then inspected. A steel reinforcement cage is lowered in, and it's filled with concrete. Drilled shafts can be enormous, reaching diameters of 10 feet or more and depths of hundreds of feet, making them the foundation of choice for massive bridges and skyscrapers. A critical on-site risk with drilled shafts is caving, where the soil walls of the hole collapse before the concrete is poured. To prevent this, engineers use a temporary steel casing or a stabilizing drilling fluid called bentonite slurry. Another deep foundation type is the pier foundation, which is similar to a drilled shaft but is typically shorter, wider, and hand-dug or excavated in a dry hole, often to reach a specific bedrock layer. So, how do you choose? The decision flowchart always starts with the geotechnical report. What is the soil profile? What is the allowable bearing pressure at various depths? What are the groundwater conditions? For a light frame house on stiff clay, a simple slab-on-grade or strip footing is perfect. For a medium-rise building on variable soil, a raft foundation might be the answer. For a skyscraper on soft soil over dense sand, a driven pile foundation transferring load via friction is ideal. For a massive bridge pier over deep water, a large diameter drilled shaft socketed into rock is the only solution. The choice is a complex balance of geotechnical capacity, structural loads, cost, construction accessibility, and environmental constraints. To summarize the key takeaways: 1. Shallow foundations like isolated and strip footing spread loads laterally near the surface and are used in good soil conditions. 2. Nat foundations are used for heavy loads or poor soil, acting as a single, giant floating slab. 3. Deep foundations like driven piles and drilled shafts transfer loads deep underground to competent strata, bypassing weak upper layers. And 4. The foundation choice is never arbitrary. It is a direct engineering response to the soil conditions revealed in the geotechnical investigation. Now I want to hear from you. In the comments below, what's the most challenging foundation problem you've ever encountered on a project? Was it unexpected soil conditions, adjacent structures limiting your options, or something else? Your real-world stories are invaluable.